In April 2025, the Shanghai Institute of Applied Physics began operations for the refueling of the experimental thorium reactor TMSR LF1. And this news caused a significant stir among nuclear energy professionals and enthusiasts. The interest is understandable. Online fuel refueling, meaning refueling without shutting down the reactor, is one of the final stages in testing the operability of TMSR LF1. And confirmation of its viability could mark an important milestone in the development of atomic energy. The point is, this new Chinese reactor has two fundamental differences from both classical and even not-so-classical reactors used today. First, it uses liquid nuclear fuel, and second, instead of uranium, it uses thorium as that fuel. Both of these differences appear quite promising and could indeed lead to a revolution in nuclear power and energy in general, if, of course, the ambitious Chinese experiment actually ends in success, which is not exactly far off, but still not very close either. But as always, let's go through everything step by step. And we'll start from the very basics, with how a nuclear reactor actually works. At the core of every nuclear reactor's operation lies a chain reaction of induced nuclear fission. During such a reaction, the nucleus of a fissile material absorbs a neutron and splits into two fission fragment nuclei, simultaneously emitting several more neutrons. These neutrons can cause other nuclei to split while releasing neutrons, and those emitted neutrons cause even more nuclei to split, and so on. It is this self-sustaining neutron flux that enables the rapid release of energy stored inside the nuclei of fissile radioactive material. For example, uranium-235 isotope with 92 protons and 143 neutrons, during reactor processing over 3 to 5 years, releases the same amount of energy it would otherwise release through natural radioactive decay over roughly 300 to 400 million years. For this to work, we need a certain amount of fissile material in the reactor core. If there is too little, the emitted neutrons will pass through the core too quickly without hitting other nuclei to trigger more fissions. This brings us to the important concept in nuclear energy: critical mass. For uranium-235, for example, it equals 50 kilograms. Secondly, in a nuclear reactor, it is crucial that on average only one neutron from each fission event initiates another fission event. More precisely, nuclear energy uses the concept of the neutron multiplication factor, defined as the ratio of the number of neutrons from one generation of decays to the number in the next generation. The neutron multiplication factor must be strictly equal to 1. If it is greater, the reactor, in what is called a supercritical state, will experience increasing energy release and may result in either a nuclear or thermal explosion. If the factor is less than 1, the reactor enters a subcritical state, and the chain reaction quickly stops as free neutrons run out over time. And since fission typically releases 2 to 3 neutrons, 1 to 2 of them must be absorbed or removed, while ensuring that one neutron on average still initiates another fission. Managing this neutron population, what nuclear engineers call neutron economy, is also known as the process of controlling reactor criticality. In a nuclear fission reaction, energy is usually released in the form of heat, so a cooling system is required to perform two of the most critical tasks. First, to collect the generated thermal energy so that it can later be converted into other types of energy, such as electricity. Most often, water is used for this purpose. It is heated, turned into steam, and the steam is used to rotate generator turbines. However, the cooling system has another key role: preventing the reactor from overheating, which could lead to its destruction. This list is far from complete. For example, reactors must also contain neutron moderators and other components we have discussed in our past videos and will definitely discuss again. But now, to save time, we will focus on the reactor design aspects that differ between traditional solid fuel and innovative molten salt types. Here is how these aspects are implemented in the most common types of nuclear reactors today, such as VVER or PWR type reactors. Nuclear fuel, usually uranium oxide, with the content of fissile uranium-235 increased from its natural 0.7 to about 5%, is manufactured in the form of pellets packed into special assemblies known as fuel rods. The reactor is filled with water, which in modern reactors serves two purposes at once. It acts as both a coolant that removes heat from the core and a neutron moderator. More precisely, the water that surrounds the fuel assemblies is usually not directed straight to the turbines to generate electricity. After being exposed to strong neutron fluxes inside the reactor, it itself becomes highly radioactive. Instead, the cooling system of modern reactors is typically designed with two separate circuits. The inner circuit water absorbs heat from the reactor and transfers it to the outer circuit water, which never enters the reactor directly. Circulation of water in both loops is maintained by powerful pumps powered by electricity from the reactor itself. To control criticality, rods made of materials that absorb neutrons well are inserted into the core. By inserting more rods or lowering them deeper, we reduce neutron flux density and reaction intensity, and vice versa. The design of molten salt reactors is both similar to and different from that of solid fuel reactors. The key difference is, of course, the fuel. Instead of a fissile oxide, like uranium oxide in solid fuel reactors, molten salt reactors use salts of the fissile element, most commonly uranium tetrafluoride. Fuel pellets are not made from this salt. Instead, it is dissolved in molten non-radioactive salt, most commonly a mixture of lithium fluoride and beryllium fluoride. This mixture of radioactive uranium salt and non-radioactive carrier salt, kept in molten form at around 600 to 700 degrees Celsius, serves as the fuel for the reactor. And this same mixture also functions as the primary loop coolant. The reactor's parameters are selected so that the critical mass is achieved only in the core area, while outside it, the amount of fissile material is insufficient to maintain the reaction. Due to the heat released during fission, the salt mixture heats up in the core, leading to a decrease in its density. The heated layers of salt rise upward. This upward flow pushes the hot molten salt out of the core into the cooling system. The molten fuel flows into a heat exchanger, where it transfers its heat to the water of the external cooling loop, which is then directed to turbines to generate electricity. The salt mixture cools down, becomes denser, and begins to sink, its weight pushing the underlying molten salt back into the core. As for controlling the reactor's criticality, it is usually done by injecting additional portions of uranium fluoride into the mixture, which increases the concentration of fissile material and the reactivity of the fuel. And if the reaction rate needs to be decreased instead, additional amounts of non-radioactive salt mixture are introduced into the reactor, which lowers the concentration of fissile material and reduces reaction intensity. Molten salt reactors have a whole set of undeniable advantages over solid fuel reactors, especially over solid fuel water-based ones, primarily in the area of safety, a key issue in the nuclear field. One of the main problems with solid fuel reactors is the risk of cooling system failure. If the pumps circulating water inside the reactor stop working, for example, due to power supply problems, circulation will cease and heat will no longer be removed from the core, which can lead to overheating, core meltdown, and serious accidents. The temperature in the active zone of VVER or PWR type reactors is about 300 degrees Celsius, which is higher than the normal boiling point of water. To keep the water from boiling inside the reactor, it must be supplied to the system under high pressure, around 150 atmospheres. This creates another vulnerability in the reactor. Strong high-pressure pipes must be used, but even these carry an increased risk of ruptures, cracks, and leaks, including leaks of highly radioactive water and/or highly radioactive superheated steam. If some of the water escapes the system, the water level in the core may drop, and the fuel rods could be left entirely without cooling. Molten salt reactors do not have these problems. The temperature inside the reactor is usually about 700 degrees Celsius, while the salt mixture boils at about 1,400 degrees. The fact that the coolant does not undergo phase transitions, even under significant heating, is already a major advantage. But even more important is that the salt remains liquid at atmospheric pressure. This allows for a simpler piping system. And that, in turn, gives salt reactors their main advantage, cooling through natural circulation within convection flows, without any pumps, whose flawless operation is a constant concern in solid fuel reactors. Moreover, if for some reason the reaction rate increases, this leads to a rise in reactor temperature. That is, to a greater temperature difference between the core and the external cooling loop. This, in turn, increases convection intensity and improves heat removal, so the reactor responds to temperature growth with an increase in cooling efficiency, automatically, without any external intervention. By the way, this is not the only passive safety system in molten salt reactors. For example, as the temperature rises, the density of the salt mixture decreases, and so does the concentration of fissile material, which leads to a reduction in reaction rate and energy output. In other words, a reactor that has overheated beyond the normal level kind of cools itself down, within certain limits, of course. If those limits are exceeded and the situation becomes unmanageable, there is another safety system, the so-called drain traps. These are special containers located under the reactor, normally sealed off from it by plugs made of the same salt circulating in the reactor, but in solid form. These plugs are kept solid by an external active cooling system. If something goes wrong in the reactor, this system can be turned off, the plugs will melt, and the reactor's core mixture will flow down into the drain tanks. This whole setup is designed so that the fissile material in any one tank never reaches critical mass, meaning the chain reaction dies out quickly once the molten fuel is drained. The melting of the plugs can be triggered manually by operators who shut off the cooling system, but they can also melt on their own due to excessive overheating, preventing the reactor from spiraling out of control. Another major advantage of molten salt reactors is their ability to operate continuously without needing to be shut down for fuel reloading, a completely unavoidable and very inconvenient feature of solid fuel reactors. When uranium-235 in the fuel rods undergoes fission, those rods must be removed and replaced with fresh ones, which requires shutting down the reactor. Ever heard in the news that a reactor has been taken offline for refueling and routine maintenance? That's exactly what it means. And it's no simple procedure. Unlike uranium, which is only weakly radioactive, spent fuel rods contain a lot of highly radioactive fission products and neutron-activated materials from the fuel structures themselves. So the rods not only have to be removed under strict safety measures, but also stored somewhere afterward. And that brings us face to face with another problem of modern nuclear power: radioactive waste. Molten salt reactors, on the other hand, do not necessarily have to be shut down for refueling. The waste products can be removed during operation by effectively filtering the molten fuel from unwanted impurities. Similarly, as the fissile material burns up, new fuel can be gradually added to the mixture, allowing the reactor to run almost continuously. And that's not just about grid reliability for the power systems fed by such reactors. It's also a matter of the stability and safety of the reactor itself. Why then, despite all these massive advantages of molten salt reactors, are we still using solid fuel ones? There are several reasons, though they all ultimately come down to the same thing: money. One of the most important drawbacks of molten salt reactors is the high chemical reactivity of the salts used in them, especially in molten form. For example, these salts aggressively corrode most metals, including steel, the main structural material in solid fuel reactors. The components of the salt mixture not only corrode metals, but also react violently with components of atmospheric air, especially oxygen and water vapor. So air contact with the reactor must be avoided at all costs. To achieve this, the reactor is usually placed in a chemically inert atmosphere, ideally helium, which is also quite expensive. Additionally, the salt's composition must be constantly monitored to prevent the formation, under radiation and other conditions, of even more chemically aggressive compounds. Not that these are unsolvable problems, but solving them does require additional spending. Alloys resistant to salt corrosion already exist today, such as nickel, molybdenum, chromium alloys like the so-called Hastelloy N and its analogs. But these alloys cost tens of times more than regular steel. significantly increasing the total construction cost of the reactors. All of this leads to higher cost per kilowatt hour of electricity produced by such reactors. 1 kilowatt hour of electricity from a molten salt reactor currently costs about 2 to 3 times more than a kilowatt hour from a solid fuel reactor. Widespread use of molten salt reactors would require the creation of an entire industrial ecosystem of supporting infrastructure. And that again means more money, and quite a lot of it. So when scientists and engineers in the late 1960s and early 70s concluded that molten salt reactors were pretty interesting, the decision makers, both in the USSR and the USA, decided it wasn't worth the trouble, especially since people were almost entirely confident in the absolute safety of solid fuel reactors at the time. The accidents at 3 Mile Island, Chernobyl, and Fukushima clearly showed that the safety of solid fuel reactors leaves much to be desired, and one would think that this would have revived interest in molten salt reactors. However, something different happened. The public, frightened by these disasters, didn't demand safer nuclear reactors. They demanded abandoning nuclear power altogether. Only in recent years, when it has become clear that we probably cannot do without nuclear energy, has there been renewed interest in new, safer next-generation reactors, including molten salt ones. And the main selling point of molten salt reactors turned out to be their near-perfect suitability for implementing a very interesting concept: the closed thorium fuel cycle. Thorium is a silvery metal from the actinide series, with atomic number 90 in the periodic table. Like all heavy elements, thorium is radioactive, but only weakly so. Global thorium reserves are estimated at around 30 to 40 million tons, meaning it is about 7 to 10 times more abundant than uranium. Moreover, unlike uranium, it is distributed almost everywhere on Earth. From the viewpoint of nuclear energy, thorium at first seems totally useless. It is almost 100% composed of the isotope thorium-232, which cannot sustain a fission chain reaction. This means that the only thing thorium can do on its own is decay naturally, slowly and silently. However, if a neutron hits the nucleus of a thorium-232 atom, the nucleus will absorb the neutron and become thorium-233. On average, after 22 minutes, thorium-233 undergoes beta decay. One of its neutrons turns into a proton with the emission of an electron, and thorium-233 becomes protactinium-233. Then, on average, after 27 days, protactinium-233 also undergoes beta decay and turns into uranium-233. Uranium-233 can sustain a fission chain reaction and can be used as nuclear fuel. So thorium itself cannot serve as nuclear fuel, but you can make fuel from it by exposing it to a strong neutron flux. And where do we find strong neutron fluxes? Right? In a nuclear reactor. The thorium fuel cycle works like this. You take a working nuclear reactor and place a certain amount of thorium inside. While the reactor operates, some thorium is converted into uranium-233. You then extract the uranium from the thorium and load it back into the reactor as fuel, along with a new portion of fresh thorium. Thus, during operation, the reactor produces not only electricity, which is what we built it for, but also fuel for its own future use. In principle, this operation can also be done in regular solid fuel reactors. The required neutron flux is available there too. But in practice, it turns out to be quite problematic. First, uranium-233, unlike its older brothers, uranium-235 and uranium-238, is quite radioactive. Also, during its production, small amounts of uranium-232 and uranium-234 are formed, which are even more radioactive and produce some very unpleasant decay products from a radiation safety perspective, such as thallium-208, a powerful gamma emitter. So, extracting uranium-233 from irradiated thorium is not the healthiest job. It requires strict safety protocols and therefore is very expensive. The advantage of a molten salt reactor is that none of this needs to be done. The whole process happens naturally during reactor operation. Initially, we load the reactor with uranium that we produced beforehand. We start the chain reaction and then gradually begin adding thorium. Inside the reactor, Thorium is irradiated and begins converting into uranium-233, which is immediately involved in the chain reaction and itself becomes fuel. As the initial seed uranium is slowly burned up, the reactor gradually transitions to operating on uranium-233, fuel it produced for itself during operation, thus completing the closed thorium cycle. What else is formed in the process doesn't matter too much. All those unpleasantly radioactive byproducts will either be burned up in the reactor core or disposed of along with other nuclear waste. By the way, in the thorium cycle, this waste is much less dangerous. For example, it contains significantly fewer so-called minor actinides and no plutonium at all. While waste from the uranium cycle remains dangerous for tens or even hundreds of thousands of years, waste from thorium reactors drops to natural background radiation levels in about 300 to 500 years. But the key issue is not waste. It's the availability and cost of fuel. There is far more thorium on Earth than uranium, and far more than uranium-235 in particular, which, as we said, makes up only 0.7% of natural uranium. According to various estimates, global uranium-235 reserves may last nuclear energy for 50 to 70 or maybe 100 to 200 years. But thorium reserves are enough to meet humanity's energy needs for 20,000 years, or by other estimates, 60 or even 80,000 years. The question of isotopic composition is also important. Natural uranium requires enrichment, raising the concentration of uranium-235 to at least 3 to 5%, a very complex and costly process. Thorium needs no enrichment. Natural thorium can simply be turned into thorium fluoride and loaded directly into the reactor. Avoiding the expensive fuel enrichment process can significantly lower the cost of nuclear electricity by roughly 1.5 to 2 times compared to solid fuel uranium reactors. We already discussed a similar concept in one of our previous videos when talking about the closed uranium fuel cycle, where nuclear fuel is to be made from waste uranium-238 in fast neutron reactors. In essence, the closed thorium cycle is an alternative to the closed uranium cycle, just with different materials and different reactor types. Russia, for instance, has chosen the fast neutron path, while China, as we see, decided to work with thorium. So what is the current status of China's thorium project? It is now fair to say that China has a functioning molten salt reactor, and that alone is a major achievement. Although, it's worth noting that China is not a pioneer in this field. Back in the 1960s, at the Oak Ridge Lab in the USA, an experimental molten salt reactor called MSRE operated successfully for 4.5 years on uranium-233. The key issue now is producing uranium-233 from thorium. The Americans didn't pursue this at all. The Chinese have tried and achieved some success, at least in the TMSR-LF1 reactor. The production of protactinium-233 has been confirmed, which implies uranium-233 is also being formed. The big question is, how much? I haven't found experimental data on this, but theoretical estimates suggest that the fuel conversion ratio in TMSR-LF1 likely does not exceed 10%. In other words, for every 1 kilogram of fuel burned, TMSR-LF1 produces only 100 grams of new fuel, which is not yet enough to close the fuel cycle. TMSR-LF1, due to its low power, cannot efficiently produce uranium-233. In higher power versions of the reactor, the conversion ratio would increase. A more serious issue is the absence of a protactinium separation system. Without such a system, it's impossible to achieve the required conversion ratio of 1 needed to close the cycle. We said that in the reactor, thorium-232 turns into thorium-233, which through a chain of beta decays becomes protactinium-233, and then becomes uranium-233. And that is exactly what happens, but only under one condition. Protactinium-233, with its 27-day half-life, must not absorb another neutron during that time. If it does absorb a neutron, it becomes protactinium-234, which then undergoes alpha decay and turns into actinium-220, and we don't end up with uranium-233 at all. To avoid this scenario, protactinium-233 must be extracted from the molten salt and placed into a special holding tank, where it can naturally decay into uranium-233. And that uranium-233 can then be fed back into the reactor. This system for extracting protactinium from the salt mixture is missing in the Chinese reactor, and it's currently unclear when it will be added, let alone when its practical effectiveness will be proven. So if we're talking specifically about a closed thorium fuel cycle, Chinese nuclear engineers are still only beginning to approach that goal. Given how long it takes to implement innovations in nuclear energy, it may still be several decades before we see a truly closed thorium fuel cycle. Nevertheless, the very fact that work is underway in this promising direction is encouraging, as is the fact that in recent years we've been hearing more and more about fundamentally new approaches in nuclear energy, a field humanity cannot do without. In our future videos, we'll return more than once to exciting projects in this area. So if you're interested in the future of peaceful nuclear power, be sure to subscribe so you don't miss anything. If you like this project, I invite you to join our supporters and help me make it even better. You can become a channel sponsor right here on YouTube or through our pages on Patreon and Boosty. The link to the latter, as well as a QR code, should be appearing on your screen right now. Huge thanks to everyone who is already supporting the project and to those who decide to join today. All the best to you, dear friends, and see you again in our next videos.